We've all heard the term of phrase flexing your muscles, but probably not consider that the International Space Station is constantly flexing its muscles, in a way. It does wiggle and move, as well as orbit in a straight line. Knowing that this occurs has an important effect on the design of experiments that are going on inside. Important question, though, is how do you measure that movement? NASA commentator Lori Meggs at the Marshall Space Flight Center caught up with the principal engineer for an experiment that has been measuring the movements of the space station since 2012.
This particular experiment that we're running here, the Flexure experiment, really is designed to capture information about the motion, about the wiggle and the flexing of the station that is known to occur at these locations, but something that's not readily available because the sensors that can measure this are not always activated, or there may not actually be sensors in the vicinity where we're operating. We're located very high in the station, and the ability to measure the flexing motion is something would be very useful to other experimenters that may have payloads that may actually be berthed near us. So that's really what we're trying to do. We're utilizing the antenna in ways not initially designed to be able to capture this data.
What is this flexure we're talking about?
The simplest analogy would be, driving a minivan with your kids in the back seat, and they push off the walls or they bounce around. You actually feel that wiggle in the car, and that's exactly what happens. When the crew is activated and they're not sleeping, they push off from the various modules to locomote themselves throughout the structure. And so when they do that push off, because space station is so very large, starts exciting what we call these vibratory modes, and the system basically flexes and moves, and you'll start to see scissoring motions. So you have this large 100-meter structure which is starting to scissor and twist and do all these bendings, and those sorts of things can play havoc with pointing experiments that may be located on these truss structures. So when we say flexure, I'm talking about sort of this twisting motion that may occur out in the far reaches of the station.
How can it be used on Earth and in space? How can the information that you glean from this?
Well, I think we're really trying to supply a piece of information for future experimenters, and so the flexing that we're trying to measure, obviously known to exist, the quantities, the frequencies, are useful for optical communications experiments. These experiments require really high precision pointing, and in order to stress their systems to be able to understand if they'll actually work, they need to be able to understand what these flexures are. And so it's important to have an understanding of what the magnitude of this is, so you can kind of prepare the experiment prior to it being launched, prior to it being flown. So I think what we're trying to do is provide useful data for future experimenters, which will in turn benefit longer duration, longer timeline activities, for instance, like optical communications for deep space pointing and things of that nature.
How long have you been on the station, and how long will this go on?
Well, we've been running since 2012. We launched in August, transited, and then were berthed and started our commissioning activities in August of 2012. And we've been operating ever since. We've been basically a continuous shift of operations. We have an operations team, and we've been supporting that, and we'll probably continue for several years to come, with new directives from the SCAM program office.
What have you learned so far?
Well, that would take probably more than this interview to conduct that. Specifically for our test here, we really, when we first ran this experiment, it was very difficult to extract this data and to make sense of it, but we've really refined that, and we now have a very good sense that we can actually use this Ka-band antenna, not originally designed to do what it is being used for, to actually conduct these types of experiments, to actually get this flexure. And we're supporting other activities. One of them is a discrete thruster firing test, and we hope to activate our payload to be able to capture that information as well, something that, again, we hadn't originally intended to do, but something that we can do.
The engineers normally track a data satellite with a Ka-band antenna, but this team has explored using the sun as a radio source for Ka-band tracking, which makes it a unique, first-of-its-kind experiment. And it's ideal because the sun is a source that is precisely known and always available.